Hello, welcome to the second part of the amines tutorial. So we're just going to be going into a bit more detail about the amines and, uh, stuffs, second video. Yep. The first thing I'll say about amines is that they're bases, and you might have guessed that from the last video. I don't think we mentioned it though. And if they're going to be called anything, they're Bronsted-Lowry bases. So a Bronsted-Lowry base is just a proton acceptor. Proton, being a hydrogen nucleus, is a proton. And I've used this example here with phenylamine. Remember, it can be anything else. It doesn't have to be phenylamine. It can be ethylamine or anything, any amine. But this is in the book, and I just copied it down. So, yeah, sinner here. But it's reacting here with hydrochloric acid, HCl, and so it's in solution with HCl. And I've drawn the ions here separately. And this lone pair, what you're really looking for here is the nitrogen with the lone pair of electrons. And so this nitrogen with the lone pair of electrons, we want to form a dative covalent bond with the hydrogen, or a coordinate bond with the hydrogen. And so it will form a positive cation. And so now it's in solution, a positive cation and this chloride ion here are in solution together. You can imagine what's going to happen. They're going to form into an ionic substance. And in this case it's called phenylammonium chloride, which is a salt, remember. So if you ever see a positive cation and a negative ion in there, an ion, then you can pretty much always assume that it'll form a salt, or they'll form ionic bonds together in most cases. You can call it phenylamine hydrochloride as well, but I think phenylammonium is easier because you've got the ammonium here, and you see that nitrogen's it's bonded to 3 hydrogens. It makes more sense to me. But you can call it whatever you want. Either one of those two works. And moving on to the next slide. We're just going to talk a bit about how the phenylammonium chloride as a salt. Oh, the video messed up before, and that black box was meant to be covering that word so that you could guess what it was. But there's a couple more later. But yeah, the program stopped working. So, amines reacting with acids. In that case, we just said that it reacts with hydrochloric acid. It'll form a soluble salt, which is soluble in water. And if you evaporate the water, it will crystallize, as you know again, because I'm sure you've been over ionic substances, salts and things, but if you do want to reform the amine back into the amine from the positive cation, the ammonium salt here, ammonium salt? Yeah, the ammonium salt. You just have to reform it by reacting it with a strong base, so a stronger base, like sodium hydroxide. The hydroxide will have a lone pair of electrons, and it'll steal this hydrogen here, and it'll reform it back into an amine. So the hydroxide will form water because it's now H2O, and the chlorine won't be bonding ionically with anything because there's no overall charge on any atoms here. So that's how you reform it back into an amine from a quaternary ammonium salt. You remember these are called quaternary ammonium salts because they're amines with 4 things bonded to them, so they're quaternary ammonium salts. But ammonium because it's ammonium because NH3. Remember, NH3 group is ammonium. And so moving on, I think that's how you form the amine from the quaternary ammonium salts. So there you go. Moving on. A strong base, what you could class as a strong base, sorry, my microphone's fuzzing erratically. A strong base is considered, I suppose if you had a scale, it's how readily it will accept a proton. So if a substance accepts a proton really well, really easily, then it's quite a strong base because it'll have a high electronegativity. And when we look at amines with a alkyl group attached to them, so this here could be like, ethane or methane or propane or whatever attached to the NH2, what happens is that the alkyl group, this bit here, will release electrons away from the alkyl group and towards the nitrogen atom. So towards the nitrogen atom here, it's represented by a little arrow on the bond here. So next to nitrogen, that is, from the alkyl group. So this alkyl group will release electrons and it will move them towards nitrogen, and so it'll have a higher electron density. What I mean by that is that because there's more electrons circling like near the hydrogen, the electron density in that area will be much higher, so there'll be more electrons there, and so you can assume it's going to have a bigger electron density, obviously. And what this is called is the inductive effect. So induction, if you've ever been over that in physics or something. So these releasing electrons towards nitrogen is called the inductive effect, and it happens to all amines if they've got an alkyl group attached to them. And this is ethylamine, if you're wondering. And so that's quite simple to understand. Just as a side note, you'll often see these amines referred to as aliphatic amines. It just means that it's got alkyl group attached to it. Nothing that fancy. If that ever trips you up or anything, and you'll see also the inductive effect represented with R, and it's got a little bond here with a little arrow, and the NH2 group. Yeah, so you'll see that too. That's just referring to the inductive effect. Moving on again. This inductive effect happens with all amines, as I just said. So here we have a secondary amine, and now it's got two alkyl groups releasing their electrons away from the alkyl group and towards the nitrogen atom here. And so these will actually have an even higher electron density than the primary, because this is primary, because there's only one R group attached to the nitrogen. This primary has a higher electron density because of the inductive effect, but the secondary one here will have an even higher electron density than the primary, because it's got two alkyl groups releasing their electrons towards the nitrogen. Okay, you can guess a name for this one. I'll move this out of the way, and then you might want to pause it, just guess a name. And the name is methylpropylamine. I got there in the end. It's quite late. Don't blame me. So methylpropylamine. So yeah, secondary amines will have a stronger inductive effect due to the more alkyl groups. But however, moving on to tertiary amines, you would think, by the way, by them having a stronger inductive effect, it means that they're stronger at being bases because there's a higher electron density, so they're more able, so that there's more of a negative charge in that region, and they'll be, as I said here, they'll be able to readily accept a proton a lot more easily because it'll attract the positive proton towards itself with a higher electric charge, because like charges attract. No, sorry, unlike charges attract. Anyway, tertiary amines. Don't be fooled. Although they do have three alkyl groups attached to them, so they're going to have a higher electron density than this nitrogen here because they've got three alkyl groups with a strong inductive effect because they're all pushing their electrons towards the nitrogen here. So there'll be a very high electron density towards this nitrogen. But if you have seen the last video, and I recommend you do if you're watching this now and you haven't, we discussed why tertiary amines aren't very good at, they're not very soluble in water. That's because they have no hydrogen, so they can't really form much hydrogen bonding between the water and the nitrogen. They can still form some hydrogen, they are slightly soluble, because they've still got a lone pair here, and the waters can still form hydrogen bonds with nitrogen, but that's about it. And you know, they're quite big as well. It's harder for them they're not very soluble in water. It's harder for them to form a solution. And so they're not strong as bases as secondary. So just remember that's tertiary amines. So you've got primary bases, quite strong bases. Then you've got secondary, even stronger. Tertiary, not as strong because they're not that soluble in water. Okay, and so it's hard. So obviously they're not going to be able to act as bases if they're not in solution with anything. And I've got black box here. Can anybody guess the name? Pause the video, just guess the name, and we'll read it now. Ethyl methyl propylamine. Remember that it's done in alphabetical order, not the chain length, so ethyl first, then methyl, then propylamine. Alphabets. Remember that from the last video. I won't go over too much detail. And so that's primary, secondary, and tertiary aliphatic amines. And onto the aromatic amines, and we'll go over our aromatic chemistry later. I've told you before we'll be doing those in another video, so don't worry if you don't recognise what this is, the benzene here. But we did go over that these are amines because they've got the NH2 group attached to them. This is just the carbons and one hydrogen, but we'll go over benzenes on each carbon. And so these aren't actually as strong a base as the aliphatic amines, so the ones with alkyl groups attached to them, like this primary here or the secondary. We'll ignore the tertiary because that's not actually a very good base anyway. But they're not as strong because the lone pair on the nitrogen here, one thing we'll learn in aromatic chemistry is the benzene ring. What it has, I'll go into more detail when we go over the topic. I don't want to like sidetrack with this too much, but they have a delocalized system of electrons above and below the ring of the carbon ring here. That's what the circle is representing. So there's a very high electron density here, and we'll explain why that happens in aromatic chemistry when we go over that. But so yeah, it might be good to go over aromatic chemistry before or after this video, just so you understand more easily. But what happens is the lone pair from the nitrogen overlaps it gets pulled in by the electron ring here, the high electron density ring that's formed in this benzene. Okay, and so it actually pulls away from the negative charge. There's no inductive effect which happens here because this isn't an alkyl group member. This will be an aryl group. Yeah, so there's no inductive effect, and it's the opposite really, but don't say that. The lone pair of electrons is pulled towards the benzene ring because of the electron density here. It overlaps, and so it actually takes away from the negative charge, and so it's less of a base. It's not as strong as a base because it can't attract protons as readily. And so there's a little thing which I've highlighted in purple here because it's quite important. Just to remember this, and you'll be fine. Ethylamine, so that's like this one here, ethylamine, is a stronger base than ammonia. And it's a stronger base than ammonia because it's got that inductive effect occurring, pushing electrons towards nitrogen, making it more negative and able to attract a proton more readily. But ammonia is a stronger base than phenylamine, which is this here. This is phenylamine, and it's a stronger base than phenylamine because the nitrogen has its lone pair of electrons. It's got that strong negative charge already, but in phenylamine that is actually being taken away, not completely, but like the negative charge is being reduced, and so it will actually be a weaker base because it's able to attract the protons less so. And so ammonia is a stronger base than phenylamine, but remember that ethylamine is a stronger base than ammonia. It's not just ethylamine, it can be any other alkyl group amine, but obviously not tertiary amines because they're not very good. They're not very strong. But moving on, so just remember that's useful to remember. Remember, ammonia is in the middle. So ammonia is kind of like, these two are like derivatives of ammonia in a way, because they've both got the NH2 here. So just remember, ammonia will be in the middle. Yeah. So moving on. Where's when it loads eventually? So now we're going to look into how you make amines. So how do you actually make an amine from ammonia? And so this is the first method we'll be looking at, is reacting ammonia with a haloalkane. You'll be happy to see this. It looks more complicated than it is. I hate this, but it's the easiest and most compact way to explain it. Is that if we have ammonia and reacts with a haloalkane, so it could be anything. I need to kind of hurry up with this video a bit, dragging on a bit. So this haloalkane could be anything. It could be like chloropropane or whatever, it will. You've been over nucleophilic substitution. I'm assuming you've been over nucleophilic substitution. If you haven't, I would recommend going over some mechanisms. But I'm assuming you've been over nucleophilic substitution. And so, as we know, the NH3 here will replace the X So it will replace the halogen, and the halogen will give its electrons to the R group, and it will form a salt because the nitrogen. But remember, it will only form a salt because the nitrogen's got when it's got four bonds, it'll have an overall positive charge, and so it'll form a salt here. This is in nucleophilic substitution. This is the only one that forms a salt and goes through the extra process that you will have learnt. And so the ammonia will react again with the salt and steal one of the hydrogens from this ammonia group attached to the R group. And I'm not going into too much detail about this because you've been over it before. Just to clarify again, you've been over this before. So if you do need to go over it, go over nucleophilic substitution with ammonia. And so that'll take away the positive charge from this and form an amine. This is the amine with an R group attached to it. And this which has now become ammonium with NH4 will have a positive charge because nitrogen has 4 bonds, overall positive charge, and it will form an ammonium salt here. Okay. I've just included this at the bottom here just to remind you of the mechanism for nucleophilic substitution. The lone pair on the nitrogen will replace the X here. It will go. The arrow points towards the carbon. Replace the X. You know, I don't have to go over this again. Well, I've been over it in the first place, but I'm sure you will have done this if you're looking at this video. So just make sure, if you haven't been over nucleophilic substitution, make sure to go over that. But I don't want to focus too much on it. Moving on. The problem with this method, moving back again, is when you react ammonia with a haloalkane, if you assume this haloalkane here is in excess, the ammonia, when it forms into the amine here, the RNH2, because it's got an R group attached to it, it'll still have a lone pair of electrons, just as it has on the ammonia, which we were talking about earlier on. I mean, you've seen enough amines at this point to know that this amine will have a lone pair of electrons, and so it'll be able to react again as a nucleophile to this haloalkane here and replace the X. And because it's ammonia again, the nitrogen will get 4 bonds and form a positive cation and form a salt, but I'm not going to explain that anymore. So it'll form a salt, and then NH3 again will come over, steal the hydrogen away, and form another amine. But this time, because it's taken another R group from this haloalkane, it's now got 2 R groups, so it's formed a secondary amine. So the problem with this is you might want to form a primary amine, but unless you react it in very, very, very controlled conditions, it's going to continue on and form a secondary amine. Okay, and then the ammonium here forms a quaternary ammonium salt with, with the halogen halide rather. And so you can kind of guess there will be a step 3 because this is still a nucleophile. It will still react with the RX again, and it will form a tertiary amine. At this point, it's still a nucleophile. Okay, so you form tertiary. Now you've got in the mix. You've got primary amines being formed. You've got secondary amines, tertiary amines, and you've even got quaternary ammonium salts being formed because it will react again, because it's still a nucleophile, it's still got those lone pair of electrons. It will react with the RX here, the haloalkane, and it will form a quaternary ammonium salt. That's where it stops. But overall, it's quite a inefficient reaction. Well, if you're aiming to get one particular product, you're gonna get like 4 different types unless you're very, very controlled reaction. And so that's the first method, not the best method. Oh dear. Are we still recording? Sorry about this. Things shut down. Hold on 1 second. And we are back, I believe. But I'll stop the video here, and I'm just gonna record again.